everyone, welcome back to the channel. Welcome to the topological sorting algorithm series. This is the very first video where we'll be discussing about the concept of topological sorting, or in other words, top sort. So we'll first start with some real world examples for as a motivation to learn this algorithm. So topological sorting occurs when there is some kind of dependencies, or let's say there is a need of order. Like, let's say we have two tasks. Then to perform the second task, I must perform the first task in the order, like performing the first task first, then the second task. So there is a certain ordering in performing tasks. In these kind of situations where there is an ordering of tasks or anything, we use top sort. So let's take an example. Let's take the example of school class dependencies. So let's take this example. So imagine you are a student at a university. You want to take this class H. Okay. Now to take this class H, you must take this class D and class E, because there is an ordering. We can take the class H only if we have taken class D and class E. And since I want to take class D and E, I have to take the class A and B. This is a prerequisite. That is, to take the class H, class D and E are prerequisites, because we have two directed edges from D to H and from E to H. So these classes are prerequisites for class H. In the same fashion, class A and B are prerequisites for class D, where class A and B have no prerequisites. So there is a certain ordering. That is, to take the class H, we must take these classes A, B, D, E. Fine. That in other words, so let's take another example. That is, let's say you want to understand dynamic programming. So to understand dynamic programming well, the prerequisite is recursion. You must know the concept of recursion, how to write a recurrence relation, how to write the base case before you memorize the result or prepare the table for the corresponding recurrence. So understanding recursion is a prerequisite to understand dynamic programming. Okay, so that's the kind of ordering. There is an ordering. Fine. So whenever we see a situation where there is a prerequisite and one task has to be done before the other task, then we can think about the top sort. Let's take one more example to understand the concept better. So let's take this example, that is project dependency. So imagine you are creating a project and there are certain tasks in the project. For instance, you want to perform task B. So you can only start task B when task A has finished. So there is a certain ordering here. You can think it like this. Let's say you have a database. Now you want to protect the database by building a authentication system over it. So first you must have a database, then you will be able to prepare the authentication system. So there is a prerequisite for building the authentication system. That is, we must have a database. So that is this is another example of top sort. Now there are lot more examples. So another example can be like, maybe there's another example like let's say we have deadlock. We have deadlock in operating system. Okay, so there are a lot of scenarios when we have these kind of situations where we have to perform a certain task before another task. Okay, so there is an ordering. So in these kind of situations, we come across the concept of topological sorting. We use the concept of topological sorting. So here in this example, if I want to write out the order in which I have to take the classes, then the order would be like, I have to take class A, I have to take class B, I have to take class D, I have to take class E, and eventually after I have covered all these classes, I would be able to take class take class H. So in this fashion the classes goes. That's the correct order from left to right. Fine. So to reach the class H, we must take these classes. That's an ordering, and this is called top sort. This is called top sort. So this situation and similar such scenarios can be modeled in terms of directed acyclic graphs, and for any directed acyclic graph we have a certain ordering, that is topological ordering, which we can compute using graph traversal algorithms like depth first search or breadth first search. Okay, now I hope you got the idea where we are going. Okay, so let's jump to the formal definition of the concept. So let's see the definition of the topological sorting. Topological sorting for directed acyclic graph, that is DAG, is linear ordering of the vertices such that for every directed edge uv, so there is an edge from u to v. Okay, these are the nodes of the graph. U must comes before v in the ordering if there is an edge like this from u to v. Okay, that's the formal definition. I hope you got what is directed acyclic graph. This topological ordering is only possible for directed acyclic graph. Why directed? Because directed graph shows that there is a dependency of a certain node over the other node. Okay, so let's say this is a node A, this is node B, so there is a directed edge here, so there is a certain ordering. We can only visit node number B if we have visited node number A. So in the order they must be listed like this, A, B, from left to right. Now why it should be acyclic, why there shouldn't be cycle in the graph, we'll discuss that later. So let's take this example, let's write the topological sorting for this particular graph. So this is a directed acyclic graph, we have directed edges between the nodes and there is no cycle, we can't see there is a cycle. So what is a cycle in a graph? The cycle in a graph is basically a situation when we have a starting node, when we have a node, let's say node number 1, and we traverse certain nodes while traversing the directed edges, and finally we come back to this node 1. Then that means there is a cycle, we are revisiting this node. So now let's write the topological sorting for this graph. Okay, so this is one of the topological sorting for this graph. So basically we start from node number 1 and node number 2. Why we are starting from node number 1 and 2? Because they have no incoming edges. We have no incoming edges for node number 1 and node number 2. That is, we don't have to traverse any node before I can traverse node number 1 or node number 2. So I simply list node number 1, then I list node number 2. Then from node number 1, I can traverse node number 3 here. So I put node number 3 here. From node number 3, I can move to node number 5. So I list node number 5 here. Then from 5, I move to node number 4. So I put 4 here. Finally, from node number 2, I can move to node number 0. Okay. So this is one of the topological sortings that I can have. So another topological sorting can be, we can write it like this: 2 1, then I can put it like 3 5 4 0. This is also valid topological ordering. This is also valid. All we just have to make sure in a given ordering is that any node u must come before node v if there is an edge between u to v. That's all. Now, which is satisfied in both of these ordering? We can see that. We can verify it. 3 comes before 4, like this. 3 comes here, it lies before this node 4. And this is true for all the nodes of the graph. Okay, that means there is no unique ordering, or there is no unique topological sorted order for the given graph. There can be more than one ordering of the vertices. Okay, now let's see the next concept. Why top sort is possible for DAGs only, or directed acyclic graphs only? So we have already understood that why it is possible for only directed graphs, because there are certain situations we want to visit some node before we visit another node, and that is only possible when there is an ordering between the nodes like this. We, c- we can visit node number, we can visit this node v only if we have visited node u. Okay, that's why it is directed graph. But why do we need acyclic directed graph? Why this top sort is not possible in cyclic graphs or directed cyclic graphs? So let's take this example. This is a directed cyclic graph. There is a cycle here. You can see why there can be any ordering. Why there is no ordering or top sort for this graph? Because in this cycle here, we move from 3 to 4, then from 4 to 5, then from 5 to 3 back. There is no starting point. There is no starting point in this ordering. There is no, we don't know where we have to start. Okay, that's why this top sort is not possible for cyclic graphs or the graphs which contains cycles. Fine. Now the next point is, all the rooted trees have a topological ordering because they do not contain any cycles. So take this example. This is a rooted tree. The root is this node number a. That means there is no incoming edge for this node number a. It is rooted at this node, and there is always a topological ordering for these kind of trees. Okay, how to get that topological ordering? So let's see that. All we have to do is just start from the nodes with the lowest level. So start from the leaf nodes here. These are the leaf nodes which I have marked, and now we know that all of these leaf nodes lie at the same level. There is no edge between these leaf nodes. Okay, there is no edge like this. There is no edge between j and f. There is no edge between f and I. Okay, they just have a parent. So we can just cherry pick these nodes. We can put them in any order. Just start putting them in any order and start listing them from right to left. So I am putting them like this: I, then j, then f. Okay, now I have listed all of these nodes. Now I move to the next level, that is this one. Now similarly pick these nodes. Pick them E, C, G, B in any order. Finally pick these nodes D and then A, because A do not have any incoming edge. Now we can see that this is a valid topological sorting. This is a valid topological sorting. It's simple in case of trees. just start cherry picking the nodes starting from the leaf nodes and up ones. So I have basically I started from these leaf nodes. I extracted all of them. I listed them here in the ordering from right to left. Then they are listed. Then I move to the nodes just above them, that is these nodes, and I list them. Then I move to the nodes that are just above those nodes, and simply I list them. In this fashion, the top sort for the trees are evaluated, which is very simple. So the top sort goes from left to right. Okay. Now that's all about the topological sorting. We have learned a few points and some applications of the topological sorting. So whenever there is an ordering in a graph, so we're given some directed acyclic graph, that means there is certain ordering, and there will be lot of scenarios in the problem statements. We will have to care about the orderings. For instance, let's say we have some imagine a situation where we have basically some flight routes. Let's say I want to reach some location C, and my starting location is location A. So to reach location C, there is a intermediate location, let's call it B. So before I move to location C, I have to move first to location B, then from B I have to move to C. So there is certain ordering in this case. Okay, and these kind of situations, these kind of problems can be modeled in terms of topological sorting. Okay, now when we'll solve more and more problems in this series, then these things will be more clear to you. Okay, now that's all for this video, and in the very next video we'll be discussing about the implementation details of this top sort. We'll be implementing this algorithm using two graph traversal techniques, that is depth first search and breadth first search. So for that, stay tuned with me, and I hope to see you all in my next video.